Okay. So we've been given the information that from the Earth to Artemis is 250,000 miles, from the Moon to Artemis is 50,000 miles, and from the Earth to the Moon is 530,000 miles. It's really officially the Orion capsule, but Orion is also a constellation. The distance from it is way bigger than the distance of Earth to the Moon. Actually, yeah, stars in Orion are many different distances. Hang on. Apparently, that's coming from all the way down to the snack bar. I don't know how loud it is down there. Of course, the whole kind of amplifies it. Okay, well, they're doing some really neat renovations to the snack bar. So it's a little inconvenient for the next several months, but it's going to be pretty neat. Some of you won't be around to see it. Come back and visit. Okay. Okay, so again, Earth to the Artemis capsule, Moon to the Artemis capsule, Earth to the Moon. So you draw pictures. And how you orient the pictures up to you. Here's Earth. Now put the Moon here. Okay, now this distance in thousands of miles. About 230,000. I think it might be a little under that, 226, 227,000. Because I think from the other data I've looked at, I haven't really looked at whether the Moon is in its perigee, apogee, or what. I think it's pretty close to its perigee. Otherwise, other numbers don't work out. Okay, violate the triangle inequality and all kinds of stuff. Okay, now Artemis is within 50,000 kilometers of the Moon. Well, 50,000 kilometers, if this is 230, that's about 1/5. So I could draw a little circle here, which is not Artemis, it's just a circle of radius 50,000 miles around the Moon. And then I find the point that's 250,000 kilometers away. Okay, I could actually find 2 points, one over here, one over here. And it would be easy to do that, just using a little analytic geometry. Just put this in the coordinates. If you want to put the origin here, put the Moon at 0, 230K. Then you have a circle of radius 230K centered at the point 0, 250K. Okay. That's going to be x squared plus quantity y minus 230K quantity squared. Let's say plus x squared plus what I just said, y minus 230K quantity squared is going to equal r squared, which is the square root of 250K. See, write out that equation. And that should be very familiar to you from elliptical calculus. Okay. If it isn't, might want to make it that way just in case. Because as an engineer, you need to be able to do coordinate geometry. Conic sections, all that stuff. Excuse me, I get choked up when I talk about this thing. And then you just write the equation. Distance from Earth to xy is yes, okay. And I'm not going to write all that out. That can be solved. It's very easy to solve. Early pre-calculus. Okay, you know from common sense that if this is 50,000 miles, and then the 20,000 miles from where the Earth is to where Artemis is, well, the difference of 20,000 miles. Okay, Artemis is 20,000 miles from the Moon. So you've got a circle here of radius 50. Okay. And you want to find the point on that circle that's 20K further from the Earth. Well, where's 20K further from the Earth? 20K further from the Earth is another circle. Might have an arc that looks like this. Okay. So this circle, not a very good circle, its radius is 250K. It's where this circle intersects this circle. So you take the equation of this circle, set it equal to the equation of that circle, solve for x and y. You get two solutions, one here, one here. And this is pretty much the way the picture looked. Everybody had Artemis out past the moon. I mean, it has to be because the moon's only 230K miles away. So everybody came up with a reasonable picture. So Artemis is here or it's here. Okay. Now I've got more information. And let's look at my spreadsheet. Make sure I'm giving you the right information. At least a little while ago, it was moving away from the moon. It was moving further from the moon at about 200 miles an hour and moving closer to the Earth at about 500 miles an hour. Okay. Now, how can we reconcile that? Well, one thing tells you is it's moving further from the moon, so it's not really on this circle. Okay. So on this circle, its distance from the moon wouldn't change. The distance from the moon's changing at about 250 miles an hour. So I say the displacement from the Earth because I don't distance from the Earth because displacement isn't a very good term to use either because displacement is a vector. And we're not on a one-dimensional scale. So I don't want to confuse the issue by that. What's the direction of the vector that describes the velocity of Artemis relative to the Earth? Oh yeah, another thing. Moon's moving about 2,000 miles an hour relative to Earth. Okay. It's a little complicated. Can we reconcile all these numbers and figure out which side of the moon Artemis is on? Okay. Now I kind of know, I think it's on this side because it's a retrograde orbit. Okay. It's counterclockwise. If it's clockwise, counterclockwise is a typical orbit. So we might do moon orbits the Earth the way the Earth orbits the sun. Okay. So retrograde is coming back this way. To get it there, we fired it from here, it went up to here, the moon came along and met it. And it went up to a distance of about 40,000 miles, like above the moon. At that point, I think maybe it was aligned with the moon, and now it's falling back. So, one, don't confuse this circle with the actual orbit of the capsule around the moon. Right now, we're just trying to figure out what's the direction of the vector velocity on this picture. Okay. So can we reconcile this? Moving further from the moon at 200 miles an hour, moving closer to Earth at 500 miles an hour. And I think we can assume the moon is on the arc of a circle. Okay. I mean, that's a first order assumption. It's not far from the arc of a circle. It never gets too far from the arc of a circle. It does, you know, orbit's a little flat. It's a little flat this way, and a little extended along this side. Okay. So can anybody make sense of that? No, I haven't tried to make sense of that either. I just got the data. So I'm going to stand up here trying to make sense of it while you try to make sense of it and see if anybody can make sense of it. Me, you, or nobody. Okay. It's kind of hard to make sense of too many things moving, but of course, you know, physics here, you know, talk about relative motion, all that stuff. And then the next question is the total mechanical energy of this thing remaining constant? That means sum of potential kinetic energies. Okay. Now we can figure out its kinetic energy. We have enough information to figure out its, well, we sort of have enough. We can figure out its potential energy relative to the moon, its potential energy relative to the Earth. That's very easy. That's not a vector quantity. We just do the big G, big M, little m over r for the moon and for the Earth, knowing these distances. Okay, so we'll get into energy analysis, but what about these vectors? Okay, now, you know, one thing that my lab has probably conditioned you to do is not worry about the lengths of your vectors. Because back when it was talking about just forces and velocities and stuff, and how all these things, accelerations, they just wanted a vector in the direction of. They said, don't worry about how long the vector is, okay? I'm not sure they ever made a transition to actually worrying about how long the vectors are. Of course, we kind of skipped a chapter, or you did worry about that, so it could be the way we set up the course. In any case, we want to make sure we've got the vectors of the right length. So what we've got here, okay, here's, I'm gonna do it here. I'm gonna draw the vectors pretty big because we can use any scale we like. Okay. We're getting further from the moon. Okay, so we could say, okay, if it's on this side, we're getting further from the moon, so along an axis from the moon toward capsule. We have a vector like this, which would be 200,000 miles an hour. Then we have a vector toward the Earth because we said this is changing at negative 500 miles an hour. And I did some comments there. Distance really can't change. But yeah, distance can make a negative change, okay? But it gets a little confusing. But that means you would have 500 miles an hour this way. 500, it's not 200,000, it's 200 miles an hour. Okay, that's pretty small, it's 500 miles per hour. Well, then you could sketch yourself a parallelogram and say, okay, then Artemis has to be moving this way. Well, that could make sense. I mean, this is not a perfect circle, and the orbit of Artemis about the moon isn't a perfect circle anyway. Okay, it's actually not even orbiting the moon exactly because it's only 5 times further from the Earth than from the moon. That ratio that we calculated, we do 1/80 times R1 over R2 quantity squared. It's very easy to derive. Comes out to be about 1/3. The moon is only exerting 1/3 the force that the Earth is. Now, these aren't force vectors, but you can do the force vectors. Okay, the moon's pulling it in this way with about 1/3 the force. The Earth is pulling it this way. Well, we'll do those force vectors. But you find that this thing's being kind of pulled in this direction. Okay. Now, whether that reconciles with the motion of the thing, maybe it does. I don't see a reason right now that it wouldn't. Okay. Now, we could also draw the same picture on the other side of the moon. And we get a vector that looks like this that could also be conceivably tangent. Okay. So from this picture at this point, I don't see a good reason to assume this versus this. Now, there's a lot of other data that I've been thinking about looking at. A lot of it doesn't make any sense because I haven't drawn the pictures. I've drawn them in my feeble head. And I eventually get to the point where I just go to sleep. Okay. Do that usually late at night, finally give up, go to sleep. Not getting a good picture. Because I don't know enough about the orbit. But also I haven't analyzed it. I think if I analyze the data a little more, I'll be able to explain it. I'm not going to ask you to do that. I'm just going to ask you to be able to do these basic calculations. Okay. Now, there are implications for the shape of the orbit. And also we could do a force diagram. So here we have moon. And Artemis. I'll use F sub m, the force exerted by the moon. And F sub e, and the force exerted by the Earth. The thing that worries me a little bit, I really don't want NASA to be embarrassed. I am going to have to work this out. This thing just keeps accelerating toward the Earth and not orbiting the moon. I think they're planning to do another orbit. The speed it's going right now is about the speed it was receding from the Earth. So it might be a reasonable speed to get attracted back to the Earth and not go around the moon anymore. The mission's supposed to last another 12 days or something like that. I'm going to take 12 days to get back to the Earth. I don't know how long it's going to take them. So whatever path it's on. Maybe it's going to come around here and swing around, and the moon's going to eventually move it over here, and then it's going to come back. If you want to hit the Earth on this side, because the Earth's rotating this way, if you hit it on this side, the atmosphere is coming at you. Whereas if you hit it on this side, the atmosphere is going away from you. Okay. You don't want to hit the atmosphere any faster than you need to. And where the Earth, the Earth is rotating at the point where they're likely, I don't know exactly where they're talking about re-entry, but it's fairly close to 500 to 600 miles an hour, maybe even closer to 700. Because of course, Earth is like this. It's rotating this way. Then points up near the North Pole don't move very fast. It takes 24 hours to go around a little circle up here. It takes later. It takes 24 hours to go around a big circle. And that comes out to around 700 miles an hour. Okay. So you're going to re-enter at a point that's not in the upper latitudes. Okay. It's going to be down at our latitude or closer. And at our latitude, cosine 400 miles an hour, something like that. Okay. don't take that seriously. It's very much off the top of my head. Okay. Now, if we are planning to bring the thing down like this and then come around to the Earth this way, using the moon's gravity to swing it out here so it can be attracted back, and so forth. Then it's probably not on this side. It's on this side in a retrograde orbit. It could be. Okay, well, you can speculate if you like. I will speculate a little more. Maybe even do a video on it if you're required to know. Okay, so now my point is, let's just say that these are the vectors. At what rate is its potential energy changing? Okay, so let's just convert. So this is speculation. Force will go like this. Thing might be on this side, and the force, that force might be like so, but I kind of don't think so. Because it's hard to see how it would be moving away from the moon at 200 miles an hour from this side. And maybe it's just hard to see. We're not seeing it right. Okay. So, question that we can actually answer. Here's kind of a picture of what's going on. Not sure exactly what's going on. And if you go online and look at a picture of the orbit and stuff like that, you can kind of see. I kind of think it's on this side. Just because of where it's been and where it was when it reached its furthest distance from the Earth and all that stuff. Okay, so what's its potential energy? If you want to use U for potential energy, that's fine. Just to keep it as clear as possible what we're talking about, I'll use PE. Plus, it's kind of a habit. When I'm teaching, I'd like to use PE. I'm doing calculations myself, I'll use U. Question, what's a potential energy? Relative to infinity. And I'll remind you of the expression up to you how you use it. Make sure you use it intuitively. So you have a potential energy relative to the moon. And relative to the Earth. So what are the expressions for the potential energy in terms of symbols? And then what numbers would you plug into the symbols? Once you've got the expression in symbols, you don't have to write it. You know, you can take the position at any time and figure out what the total potential energy is. Also know how fast it's moving. Moon's moving about 2,000 miles an hour relative to Earth. And it turns out that the capsule's moving at a little while ago, it was 1,975 miles. So just think back to 1975, think about what you're doing in 1975. No, you weren't doing it in 1975, were you? You youngsters. Okay. That was already old in 1975. Stop showing off. Okay. Anyhow, go on. Okay, so total potential energy is fairly straightforward. It's big G, big M, little m over Rm. It's big G, big M, little m over Re. Of course, we can factor out the big G, big M, little m. We have this, okay? Now, let's just talk about the rate of change, which would be the derivative with respect to time. Okay. What's the derivative with respect to time of 1 over R? Or by the chain rule, I'll write it out in this form because that's probably the form which you're most familiar with. I'm just trying to figure out what notation is going to give you the clearest idea here. So a little more loose rod. One over R is changing with respect to R, and we'll use R in here. And you're going to multiply that by dr dt. And you're going to end up with negative 1 over R squared dr dt. It's a chain rule. If it was 1 over t, your derivative would be negative 1 over t squared, right? Because you're taking the derivative with respect to t, but R is a function of t. You got the chain. The other way to write that out is this point. You got that derivative of R with respect to time in there. It appears here as a factor. And of course, the derivative here is with respect to R. So you're still going to get the negative 1 over R squared. One way or another. That would be the derivative with respect to the radius of the moon, or the distance of the distance to the moon. And you'd have the analogous expression here. So the derivative would end up like this, just using the chain. Okay. So you can see the chain go this way, you can see it this way. Again, you have to use the chain rule because you're not taking a derivative with respect to R. The rate of change is with respect to T. R is a function of T, and this is a function of R. Okay. At RM or RE. Okay, well, you know what RM prime is? Do we have that data? Okay, that's what we tried to tell me is the speed. And I couldn't understand the word speed just hearing them. Nothing wrong with what was said. I got close and then I understood. Okay, so right there is a formula that allows us to determine the rate of change of potential energy given these two distances and the rates at which they're changing. What's the rate of change of RM? Well, it looks like 200 miles an hour. Okay, rate of change with respect to time. And implicitly, this is a time derivative, okay? So now we have RM, we have RM prime, and of course we have RE and RE prime is right there. Okay. So we can calculate the rate at which potential energy is changing. Can we calculate the rate at which the kinetic energy is changing? Well, it ought to be equal and opposite to the rate at which potential energy is changing. Okay. The net potential energy is decreasing. Things moving toward the Earth faster than it's moving away from the moon. And that ratio, 1 over 80 R, 1 over R2 quantity squared, it just comes from the the gravitational force of the moon divided by the gravitational force of the Earth. Okay, at a given distance. Earth is exerting about 2 or 3 times as much force as the moon is. Okay. So the thing's potential energy should be decreasing. It's moving toward the Earth faster. It's moving away from the moon. The Earth is exerting a greater force than the moon is. And you multiply the force by the velocity to get the rate at which your potential energy is changing. Okay. Try to understand that. Okay. The kinetic energy is changing. Okay, I didn't give you that data. but we got data. It was well, it was 1949. Remember 1949. It's the year in which I crossed the street to play with Janie, looking both ways. There's a bus 2 blocks away. Said, well, I got plenty of time because I knew physics. Okay, went over to play with Janie and got smacked for that because I was 2 years old. I wasn't supposed to be crossing streets by myself. Okay, so that year is pretty clear in my head. That's miles per hour. Then got to look at my spreadsheet, so I don't have to look at my original data. If I know where to look in the darn spreadsheet, there was a 2 hour and 31 minute (1975 miles an hour). Okay. So you can calculate change in kinetic energy. In terms of little m, this is in terms of little m, right? I think it's around 1,300 kilograms, something like that. And I'm not sure if that's just one part of it or the whole thing. Anyway, whatever it is, that's little m. If you want to figure out how much fuel you need to burn to change its velocity, you'd better know what little m is. Okay. Those are all calculations you can easily do, aren't they? Okay, so say that this calculation, this mystery, it's still a mystery. I don't know how it's going to work out. Okay. Because there's still some things that need to reconcile here. I'm not going to mention all of them. One of them is that the moon is moving at over 2,000 miles an hour. And if this is an absolute velocity relative to the Earth, not away from, not toward, that total velocity, total vector velocity, this vector, and that 2,000 mile an hour vector represents velocity. It's a little over 2,000 miles an hour. I calculated that in my head a minute ago. Check me on it. Average distance of the moon from the Earth is about 238,000 miles, 239,000. Just call it 240,000. Okay. So the circumference of the orbit is 2 pi times 240,000 miles. Okay. That comes around 1.5 million miles. You divide that by the number of hours in 28 days, which is the approximate time it takes the moon to make an orbit. And you come out, I think, with a little over 2,000 miles an hour. So this is less than the velocity of the moon, which would be consistent with the thing being on this side orbiting in this direction. Okay. Although the total of these velocities, net velocity might be 600 miles an hour, that might be enough with the Pythagorean theorem and stuff to bring that 2,100 miles an hour down to 1,975 miles an hour. So maybe that's where it is. A little hard to see how it gets into retrograde orbit, having been that far from the moon. And it doesn't look right. But I don't know. Bunch of numbers, draw pictures, and figure it out. Okay? You've got all the tools to do it. But that might be a little bit of a stretch. Should be pretty easy for me. Probably won't be, but it should be. Okay. The whole idea, looking at a lot of physics, we're looking at relative velocities, we're looking at potential energies, we're looking at kinetic energy changes. Okay. And we got a derivative interest. Does all this work? Does it reconcile? If when you plug the information into this formula that we've derived, or something that you look up on the internet, okay? Does that reconcile with this change in velocity? This is clearly decreasing as at 500 miles an hour toward the Earth, or closer to the Earth. Doesn't matter if it's toward or, you know, arcing closer to the Earth. Only the proximity to the Earth affects its potential energy relative to the Earth. And the 1/2 mv squared for this, just convert to meters per second. That's going to be about around 800 meters per second. Between 800 and 900. And so will that, but easy to calculate. Easy to calculate that. So I'm going to ask you to do those calculations before lab Friday. Okay. Then we'll figure out how to arrange magnets to make the thing orbit the magnets. We can do a model and show off to NASA because we were able to make something orbit a magnetic field. That's really okay. It's not an inverse square. Okay. And now we're going to switch off over to the idea of simple harmonic motion. And we've seen a simple harmonic motion of the beam about its axis. It kind of oscillates back and forth, right? Does that spontaneously with this setup, because no matter how you set it up, it's going to be unbalanced a little bit. And what's going to happen is, well, its gravitational potential energy is going to decrease, its kinetic energy is going to go up. In other words, there's going to be a net decrease in the average height of the mass as it speeds up, and a net decrease when it starts going back up. Now that's easiest to see if you hold it like this. Okay. Okay. Yeah, what happens to potential energy? From here to here, well, average position of every mass decreases, or in a little more sophisticated formulation, the center of mass descends. And the change of potential energy is just the product of the mass times the distance at the center of mass descends. Okay. This is related to the forces. And what's the force here? Well, actually, it's torques in this case. There's a torque exerted by the center of mass. And using the incredible strength of my fingers, I'm able to resist that for a short time. Okay. Center of mass is right here. Gravity's acting down. The moment arm is the distance of the line of action to the pivot point, the axis of rotation. As this thing descends toward its equilibrium position, that moment arm changes. The force doesn't change, but the moment arm changes. So the torque decreases, ends up at 0 here. The torque is proportional for small oscillations to how far your, well, let's say to your angle. Okay, if theta is the angle with vertical, your torque is proportional to theta. It's actually depends on the sine of theta, and the sine of theta is very close to theta when theta is small. Okay, well, we can say then that assuming there's no friction around the pivot, of course there is, and my fingers holding it. Then in the case of the beam rotating on those good bearings, there's still a little friction. Okay. But the net torque equals A theta. It's some constant times the angle. That constant just depends on the mass. Okay. And the length, the distance of the center of mass from the pivot point, basically. Okay. So the K is just a constant we can easily measure. We'll do this in lab. You take my word for this. Okay. Also, Newton's second law for rotation, just like Newton's second law for forces, where you have force equals mass times acceleration, you have net force equals mass times acceleration. And the formal connection, well, you see the work you've done on rotation, just refreshing you on the rotation. Well, alpha is a second derivative of theta, right? So tau net equals K theta double prime. And losing my ability to do anything that involves theoretical accuracy. So I alpha is equal to K double prime. I alpha is, well, yeah, it is I alpha, but it's underwriter. I alpha is I theta double prime. So we have I theta double prime I theta double prime equals K theta, and that in turn, I mean, each of these is equal to tau net. Okay, so theta double prime equals K over I times theta. Now, if you're taking differential equations, you ought to immediately see how to solve that. I mean, among other things, you could let theta equal e to the I, or e to the RT, and solve this. And you're going to find that you have e to the I omega t. Omega is the square root of K over I. Okay. So that's trivial. One way or another, if you know differential equations, of course, most of you are in differential equations, not everybody is. So if you're sitting there lost in what I just said, well, it didn't take long to say it, so you didn't stay lost for long. This is so. If theta equals a cosine of omega t, or omega equals k over I. Meaning that your motion is governed by this cosine function. Could also be a sine function. Okay. And we'll, we get the generalized constant. Could also be written as a cosine of omega t plus some theta. So we'll get into that. But this is the basis for simple harmonic motion. This is why simple harmonic motion occurs. And you got cases of this throughout the universe, all the way from the quantum level on up. Okay. The idea is you have a restoring torque, and I don't have a negative sign in front of there. Everything I said is false. It's a restoring torque. Okay, the torque is in the opposite direction of theta. Pull the thing out this way, the torque is back that way. Same for a pendulum, simple pendulum, in which case you can do with forces. Your force would be K times X, if X is how far you pull it back. We'll talk about that. Main thing, make sure you understand this. Because the first simple harmonic motion we're going to measure is a simple harmonic motion of that beam. Because it moves slowly. Okay. Now we can actually get into the details of its simple harmonic motion. Okay, much like clerical. Now that is I alpha. It's the restoring torque that's equal to negative K theta. It's what I said, it's not the way I wrote it.